Alright, hello everyone, welcome back to class. Today we are going to be looking at a very important topic in physics, which is electric field flux and Gauss's law. Now we are going to be treating these two topics simultaneously. But firstly, I will be looking at this electric field flux. What is the meaning of electric field flux? Alright, electric field flux can be defined as the total number of field lines that it has set a given surface, or is defined as the number of field lines that emanate from a given surface with a known area. And mathematically, if I want to define this field flux, we take the field flux as the product of electric field times the area in which that field is emanated from. Now, let's look at this formula. Now, this symbol is phi to the subscript of E denotes electric field flux is equal to the product of electric field and area of that surface in which that electric field is coming from. Now, we have a cosine theta here. Now, why is that cosine theta there? Now, it might be that this field leaving that particular surface will be making an angle theta to a perpendicular line drawn to the surface or drawn to that surface area. Look at what I'm trying to say. Let's say we have this surface, let's say we have this surface, let's say we have this surface, rectangular surface. Then let's say we have electric field lines coming this way. Let's say they are radially outward. The electric field lines are outward and just leaving this surface. Now, the angle theta is the angle between these field lines and the line that is perpendicular to this surface. Let's say a line of this nature, perpendicular line to this surface. So let's say this perpendicular line is making an angle of 90 to the surface, making an angle 90 to this surface. So the angle between these field lines and that line perpendicular to the surface is one called theta. So that is the theta we're talking about here. That is the angle theta there. So generally, if you want to define the electric force, just take your E times your A cos theta. And if theta is equal to 0, if theta is equal to 0, then the flux will be equal to E times A. That is, if theta is equal to 0, it means the surface, the field lines will now be something like making an angle of 0 to the perpendicular line to that surface. You can make an angle of 0 degree, and if you just turn this surface now, so that this line and these field lines will coincide, then the angle between them will be 0, then the electric field flux will be equal to EA, because cos 0 is equal to 1, then 1 times this should give you that. So that means this field line is actually somehow parallel to the surface. Parallel to the surface. Let's look at anti-parallel condition. Let's say if our theta is equal to 180 now, that's equal to 180 degree, then our EA, our flux, which is the phi sub of E, will be equal to, if we put 180 here, we're going to have minus EA. That's what we're going to have. Because cos 180 will give us minus 1. Then, if our flux is positive, it means they are outward. If they are negative, it means it's inward. It's inward. Take note of that. If electric field flux is positive, it means it is coming outward. Then if it's negative, it means it's coming inward. Now let's look at the case of in which the field lines and the surface are not perpendicular to each other. If our theta is equal to 90 degrees, the angle between this perpendicular line to the surface and the field line, let's assume the two angles are not perpendicular. They are now making an angle of 90 to each other. Then we're going to have something like our flux will now be equal to 0, because cos 90 will give us 0. So if this perpendicular line to this surface is perpendicular to the field, then our theta will be 90. Then the flux will be 0. If this line is parallel to this field or making an angle of 0 to the field lines, the surface is something like, let's say the surface, or this, let's say this field line now is just something like coinciding with this line, our theta will be, our EA, our theta will be 0, and E, phi sub of the A will be equal to what? 180. Let's assume you now turn it upside down, so in the sense that this this surface is making an angle of 180 to this line. Then you have minus EA, which is, you can also take it that the angle will still be something like, let's say, it's still something like form of, they are coinciding, they are still parallel, but it's something like anti-parallel. They are not parallel in different directions. Let's say the direction now is something like this. It's not the line like this, it's still not like this. There are two parallel lines, but the two parallel lines are in different directions. If you have two parallel lines like this, the angle between them is 180 degrees. But if you have two parallel lines like this, let's say both of them are in the same direction, the angle between them is 0 degrees. That's it is. So both of them are parallel, 0 and 180. But one is in opposite direction, and the other one is in the same direction. Take note of that. Take note of that. So the SI unit, okay, where this is called electric field flux, this phi sub is called electric field flux. Then this E is called electric field strength or electric field intensity. Then A is the area of the surface in which these field lines are coming from. Then cos theta, I've already explained that. So this theta can be 0, it can be 180, it can be any, but if the theta is not given, you are assuming to be 0. Then you just take your E, your phi sub to E, or your flux is equal to E times what? E. Now, let's look at the question. Remember, area of the circle is pi r square. Area of the rectangle is length times breadth. Area of the square is L, length square. Take note of all these things. Let's say the surface is, let's say it's a circular shape. So you calculate the area, you should be able to do that. It's very, very important. Now, let's look at this first question. An electric field of 500 volts. Okay, before I even go to this place, let's look at SI units. Now, the SI unit of electric field, remember the SI unit of electric field is what? Newton per coulomb or volt per meter. You can also use volts per meters. Then, electric field of area, the SI unit of area is equals to meter square. Take note of that. The SI unit of area is equals to meter square. Then, cosine theta don't have any, it's just a constant number. Cosine theta is a constant value. Then our phi sub E, which is the flux, has a unit of either Newton meter square per what? Per coulomb or voltmeters. So let's look at this question now. Let's look at some properties of electric field flux. I already said, if the flux is positive, means the field lines are radially outward or coming outward from the surface. Let's say you have this board now, means the field line is coming out of this board, is leaving the board. That means if the flux is positive. But if the flux is negative, and what you have here now, it means the field line is inward. That is the direction of the field line is inward, or is going into the surface. Then electric field line is also electric field flux, not electric field line. Electric field flux is also a scalar quantity. Take note of that. Electric flux is also a scalar quantity. So I can give you, if I give you electric field line as a vector, and I give you this area as also a vector, you can just take your electric field flux as the dot product of electric field lines and this area you are seeing here. If both of them are given as a vector. If I give this area direction now, I give the electric field direction, I just take the dot product of the two to get your electric field flux. The electric field flux is a scalar quantity. Take note of that. It's very, very important. Now, let's look at a few examples. Okay, now let's look at this question. An electric field of 500 volts per meter. An electric field of 500 volts per meter makes an angle of 30 degrees. To a surface vector. Makes an angle of 30 degrees to a surface vector whose magnitude is 0.500 meters squared. Whose magnitude is 0.500 meters squared. Obtain the electric field flux leaving this surface. Obtain the electric field flux leaving this surface. I repeat, an electric field of 500 volts per meter makes an angle of 30 degrees to a surface vector whose magnitude is 0.500 meters squared. Obtain the electric field flux leaving this surface. Now, from that question, our theta is equal to 30 degrees. Then our area, because area was not mentioned in the question. But if you look at this arrangement, if you check them dimensionally, the unit of area is meter square. The unit of area is meter square. If you check the unit of this surface vector, that is a meter square. So automatically, this surface vector and area are the same thing. So I'm going to use this one as an area. Since it's a meter square, we're going to have 0.5 meter square. Then our electric field is what? 500 volts per meters. Then the electric field flux, as defined above, is EA cos theta. E times A cos what? Cos theta. What is E? 500. What is A? 0.5. And cos what? Cos 30. You did it very well with your calculator. I think you are going to have a definite answer, average answer of 217 volts meters. That's what we're going to have. 217 volts meters. So that's just that. Question 2. I hope this one is clear. Just try to look at it again. It's a very simple thing. Now let's look at this second question. Let's look at this second question. Consider a field. Consider a uniform electric field. Consider a uniform electric field of E equal to 3 times 10 raised to the power of 3 Newton per coulomb. 3 times 10 to the power of 3 Newton per coulomb. Full stop. Obtain the electric field flux. Obtain the electric field flux coming out of a squared surface. Coming out of a squared surface of side 10 cm. Coming out of a squared surface of side 10 cm. Parallel to this surface. Parallel to this surface. Remember, when the field is parallel to the surface, the angle between them is 0. And the flux automatically be equal to what? E times what? Times A. But there's no area. The length of the square was given. Now, what is the area of a square? Area of a square is L squared. Or L times L. That's the area of a square. So, we are going to have this one is same as 10 over 100 is 0.1 meter. 0.1 meter. Then, this is going to give us 0.1 squared. Or 0.1 times 0.1. That's what we're going to have. It will be 0.1 times 0.1. So this is going to give us 0.01 meter square. That's what we're going to have. 0.01 meter square. 0.01 meter square. Now, the electric field flux will be equal to electric field, which is 3 times 10 power 3 times the area of that squared surface. Now, look at what we are trying to look at here. The surface they are describing is a squared surface. So it's something like this. And the side is 10 cm. To calculate the area of the surface now would be L times M, which is L squared. That's the area of the surface. And 10 cm is 0.1 meter. So you just impute 0.1, then you're going to have that. So times 0.01, and that's going to give us a very good answer. The answer for that will be flux equal to 30 Newton meter square per coulomb. That's what you're going to have. That's your answer. 30 Newton meter square per coulomb. Now, let's look at Gauss's law. Let's look at Gauss's law. Alright, Gauss's law. Now, let's look at this second aspect of today's class, which is Gauss's law. Now, what is the meaning of Gauss's law, and why do we need this Gauss's law in this topic? Now, Gauss's law is a law that helps us to calculate the electric field flux leaving a closed surface without regards to the area of that surface. Now, we have some surfaces in which to calculate the area, their area, will be very, very difficult. So, if you want to come from the angle of Gauss's law, you don't need the area of the surface, and you will still be able to get the flux leaving that surface. Now, what is this law stating? The law states that the total total number of electric flux or the electric field flux emanating or leaving a closed surface is equal to the total number of electric charges inside that surface divided by the permittivity of free space. Divided by what? The permittivity of free space. Gauss's law states that the total number of electric field flux emanating from a closed surface or the total number of electric field lines emanating from a closed surface or the electric field flux leaving a closed surface is equal to the net charge on that surface divided by permittivity of what? Free space. Divided by what? Permittivity of free space. Mathematically, electric flux will be equal to net charge divided by E naught, where E naught denotes the permittivity of what? Of free space. Permittivity of what? Free space. And this is the value. This is value 8.85. That's just from minus 12 Coulomb square per Newton meter square. Per Newton meter square. That is the value of the permittivity of free space we're talking about. So in this question, what will solve if I ask you now, what is the total number of field lines leaving a surface with 1 coulomb of charge? What do you have to do? Put 1 coulomb of charge and divided by this. That is the answer. So what you need in this question is just your net charge. Now, from the properties of charges, it shows that charges possesses additive properties. Now, what's the meaning of that? It means that charge bodies can be added together. Like for example, if I have Q1, Q2, Q3. Okay, let me look at this. Let me look at this question. Let me look at this question. Alright. Okay, before I look at that question, I want to present this law in different ways now. Remember we said before that electric flux is equal to EA. Remember we said it before. Now, if flux from Gauss's law is Q net over epsilon naught, Q naught means net or total charge, epsilon of Q net. Epsilon naught means permittivity of free space, and this is the value here. This is the value of permittivity of free space. We said from definition, our electric flux is equal to electric line times what? Area. Now, if this is equal to this, you can say this is equal to this. So, therefore, from Gauss's law, you can say EA is equal to Q net over what? Over epsilon naught. That is impossible. This is impossible. So if I want to calculate any field of any surface now, all I have to do is to divide the net charge over the area and what? The epsilon of which is permittivity of free space, if I can calculate the area of that surface. But if I want to calculate any field flux of a given surface and I don't know the area of the surface, I can use this formula if I know the net charge on that surface. Considering the below surface, or consider the below surface shown. Look at what we're having. Look at the surface we're having. We're having this surface. And we have 2Q, 3Q, minus 5Q. We have Q here. Obtain the total flux leaving the surface. Obtain the total flux leaving the surface. So if I ask you what is the total flux leaving the surface, and you check how many times do you have here? We have 1, 2, 3, 4. The next thing you do, just calculate what is the net charge. Let that be the total. Add everything together because charges can be added together. So we're going to have 2Q plus 3Q plus Q plus minus 5Q. So we're going to have something like 2 plus 3, that is 5, plus 1, that is 6. We have 6Q minus 5. The plus is going to give us minus 5Q. Now give us Q. That's what we're going to have. 2Q minus 5Q give us Q. So the flux leaving surface will be Q net over epsilon naught, which is the Q net is Q over epsilon naught. That will be the answer. Now, why won't I use the value of epsilon naught here? Because the value of the charge is not known, but the charge is given in terms of Q. In terms of Q, Q may be maybe 9 microcoulomb and so on. In terms of Q, that's how we give this charge, we give this charge. So, since the value of Q is not given, it's better you don't leave the epsilon naught that way. So, this will be the total flux leaving the surface. Now let's look at a polythene bag. Let's have a polythene bag. Let's have a polythene bag carrying different charges. Let's have carrying different charges. 3Q minus 10Q plus 17Q plus 17Q minus 20Q minus 20Q minus Q. And they said, what is the total flux leaving this surface? He said, what is the total flux leaving the surface? what you want to do to get the net? What's the net charge on that surface? The net charge will be 3q plus minus q plus minus 10q plus 17q plus what? Minus 20q. This plus this plus this plus this plus this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The next one I do have will be 3q minus q minus 10q plus 17q minus 20q. So minus will give us, okay, let's just solve the plus first. 3 plus 17, that will give us 20q. Then minus, that will give us minus 1 minus 10 minus 11 minus 20 minus 31q. That will give us minus 11q. So therefore, the total flux leaving that surface, will be 5 sub P is equals to net charge is equals to minus 11q over epsilon. That is total flux leaving that surface. Now, we also have the application of this Gauss's law. How is it applied? Or where do we apply it? Now, the following are the applications of Gauss's law. Number 1, to calculate the electric field due to a charged wire. Calculate electric field due to a charged wire. If you have a wire that is charged, how do you calculate the electric field due to that wire? Gauss's law will help you to do that. And if you come from Gauss's law, the electric field due to a charged wire will be equal to lambda over 2 pi epsilon naught I. Lambda over 2 pi epsilon naught I. And what's lambda? Lambda defines a quantity that we call linear charge density. Linear charge density is charge over length. Charge per unit length. That's lambda. And the unit is coulomb per meter. That's the unit. Coulomb per meter. So lambda is called linear charge density. And it's charge over length. The charge of the material over the length of that material. How is the distance between the field and the wire? This out here. This is the distance between the field and the wire. Epsilon naught, they are still the same thing. Pi is 3.142. That's pi. 2 is 2. E is the electric field due to this wire we are talking about. Electric field due to this wire we are talking about. So if I ask you, what is the electric field due to a wire? We do this way. If I ask you, what is the electric field due to lines of charge? We do this way. And if any line of charge carries also charge, what is the electric field? I can solve this way. Now from here now, I can decide to make my linear charge density the subject of the formula. By multiplying this denominator to this E, then the linear charge density will be equal to 2 pi epsilon naught R times what? Times E. That's what we're going to have. Number 2. Secondly, we can also look at electric field due to a charged cylinder. Now, how do we calculate electric field due to a charged cylinder? Now, the electric field due to a charged cylinder is given by E is equals to lambda over 2 pi epsilon naught I. Lambda over 2 pi epsilon naught I. Is still the same thing as the electric field due to a charge, while both of them are equal. Now, we have electric field due to a charge sheet or a sheet of charge. Electric field due to a charge sheet. Electric field due to a charge sheet. And if I calculate electric field due to that charge sheet, it's going to give you we do calculate electric field as follow that E is equals to delta over 2 epsilon naught. Delta over 2 epsilon naught. Now, where this delta denotes a quantity, this delta here denotes a new quantity that we call area charge density. Area charge density, some people look at the surface charge density. Area charge density and is defined by charge over area. Charge over area of the surface. Charge over area of a surface. And the unit is coulomb per meter square. That's the unit of area charge density. Coulomb per meter. Remember, this lambda, the lambda is coulomb per meter, and this delta you are seeing here is what? Coulomb per meter square. Take note of that. This one is area charge density. This other one is what? Linear charge density. That's linear charge density. That's area charge density. Now we also have electric field due to a charged sphere. Electric field due to a charged sphere. And if I calculate electric field due to a charged sphere, from Gauss's law, electric field due to a charged sphere will be equal to KQ over rho squared, or Q over 4 pi epsilon naught r squared, where r rho is equal to the radius of the sphere. Where r is equal to the radius of the sphere. Where r is equal to the radius of the sphere. Now, there is something that we call area charge density. Take note of that. There's something we call linear density. Take note of that. If you need to lines of charge wire, a charge cylinder, a charge sheet, and a charge sphere. Now, if I now give a question, or we are not faced with a question, and we now want to obtain the electric field due to a charge sphere and so on, how are we going to do this? How are we going to do this? Now, let's look at this question. Question 1. Question 1. Question 1. A sphere of radius 30 cm. A sphere of radius 30 cm. A sphere of radius 30 cm holds a total charge of 10 microcoulomb. Holds a total charge of 10 microcoulomb. Holds a total charge of 10 microcoulomb. Obtain the electric field due to this sphere, and that is electric field at the surface of the sphere, and the area charge density of this sphere, and the area charge density of this sphere. Now I'm asking, what is the electric field at the surface of the sphere, and the area charge density of the sphere? That is the two questions I'm asking. Now we said electric field is equal to KQ over what? R squared. That is, what is our Q? And what is our K? And what is our R? Then the K is 9 times 10 raised to power 9 Newton meter squared per coulomb squared. That is our K. And Q is also equal to 10 microcoulomb. That is 10 microcoulomb. That is 10 times 10 raised to power minus 6 coulomb. Because micro means 10 to the power minus 6. And our radius, the cycle, is 30 cm. It has 30 over 100, that gives us 0.3 meters. Then the electric field is KQ over rho squared. That will be 9 times 10 to the power 9 times, what is Q? 10 times 10 to the power minus 6 divided by 0.3 squared. So if you solve this, we are going to have 1.0 times 10 to the power 6 Newton per coulomb. This will be the electric field due to the sphere. Then the next one is the area charge density of the sphere. The area charge density is charge over area. The charge of the sphere divided by the area of the sphere. Now, area of a sphere is simply as 4 times area of a cycle. That's the area of a sphere. 4 times area of a cycle. Area of a cycle is pi rho squared. That's the area of a cycle. The area of a sphere is 4 times that area of a cycle. So therefore, for a sphere now, this will be equal to Q over 4 pi rho squared. That will give us Q is 10 times 10 raised to the power minus 6 divided by 4 times pi. Pi is 3.142. Pi is 3.142 times 0.3 squared. So this will give us approximately 8.84 times 10 to the power minus 6 coulomb, or 8.84 microcoulomb. This is what we're going to have as our answer. So this is solution to that question. Now let's look at the next question. Look at the next question. An infinite sheet of charge. An infinite sheet of charge holds a surface charge density. An infinite sheet of charge holds a surface charge density of 3.55 times 10 to the power minus 12 coulomb per meter squared. Holds a surface charge density of 3.55 times 10 to the power minus 12 coulomb per meter squared. Calculate the electric field at the front of this infinite sheet. Calculate the electric field at the front of this infinite sheet. Or calculate the electric field at the front of an infinite sheet of charge holding a surface charge density of 3.55 times 10 to the power minus 12 coulomb per meter squared. Now, from our analysis, the quantity that has unit of coulomb per meter squared is called area charge density. So our area density now is 3.55 times 10 to the power minus 12 Coulomb per meter square. Because the unit is the unit of area charge density. The next we're going to do for a sheet of charge, electric field due to a sheet of charge is area charge density over 2 epsilon naught. It should be equal to 3.55 times 10 to the power minus 12 divided by 2 times 8.85 times 10 to the power minus 12. So we solve that very well. You are going to have approximately 0.2 Newton per coulomb. That will be the electric field in front of that infinite sheet of charge. Simple as ABC. Simple as ABC. So, let's look at this question. Next question. This question. A uniform charge conducting sphere. Take note of the name of the material. That is very important. A uniform charge conducting sphere. A uniform charge conducting sphere of 1.2 meters diameter. Of 1.2 meters diameter. That is the diameter of the sphere. Take note of that. Of 1.2 meters diameter. Hold a surface charge density of 8.1 microcoulomb per meter square. Holds what? A surface charge density of 8.1 microcoulomb per what? Per meter square. Per meter square. Obtain the charge on this sphere. Obtain what? The charge on this sphere and the electric field flux. And the electric field flux leaving the surface of the sphere. And the electric field flux leaving the surface of the sphere. Obtain the charge on this sphere and the electric field flux leaving the surface of what? Of the sphere. Now the diameter is 1.2 meters. And radius is always diameter over 2. Diameter is the line that divides a sphere into two equal parts. Or that divides a cycle into two equal parts. And the radius of that cycle will be the diameter divided by 2. So diameter over 2 gives us radius. So this is going to give us 1.2 over 2. This is going to give us 0.6 meters. That is the radius of the cycle. Now, what about there's a quantity here given which is in coulomb per meter square. I told you the quantity in coulomb per meter square is called area charge density. So that's 8.1. Micro means 10 to the power minus 6. That's of micro in coulomb per meter square. Now we said area charge density is equal to charge over what? Over area. Then what is charge? Because they said what is the charge on the sphere? What will be the charge now? The charge will be equal to area times what? Area charge density. So what is the area of the sphere? For a sphere, area is equal to what? 4 pi r squared. That is the area of the sphere. I've done that before. Then our charge will now be equal to 4 pi r squared times what? That is delta. So this will give us 4 times pi times 0.6 squared times 8.1 times 10 to the power what? Minus 6. So this will give us 3.66 times 10 to the power minus 5 coulomb. 3.66 times 10 to the power minus 5 coulomb. Or 36.6 microcoulomb. Or 36.6 microcoulomb. If you move this point to this side, now you move one from this minus 5, give you minus 6. 10 to the power minus 6 means micro. So it's going to be 36.6 microcoulomb as well. Then the total flux leaving the surface of the sphere now will be the total charge over what? Epsilon from Gauss's law. Or you can use KQ over rho square, which is the electric field due to this one is not even electric field, so we're looking at the total charge of the sphere. So we can also use EA. If you know the electric field due to this sphere, use to multiply the area of this sphere, we also give you this answer. We want to do now. Remember, for this Gauss's law, we don't use area. Or just leave the charge on the sphere. And the charge on this sphere is what? 3.66 times 10 to the power minus 5. What is the epsilon of 8.85 times 10 to the power minus 12? So if you solve that very well, we're going to have 4.14 times 10 to the power 6 Newton meters per coulomb. This is AD. Total flux leaving the surface of the sphere. What will be the total flux leaving the surface of what? Of the sphere. Now, that is just that. Now let's look at the next question. Next question. I'm going to solve questions in this topic. I'm going to solve questions. Next question. An infinite line of charge. An infinite line of charge. An infinite line of charge produces a field of 4 times 10 raised to the power 5 Newton per coulomb. An infinite line of charge. An infinite line of charge produces a field of what? 4 times 10 raised to the power 5 Newton per coulomb at a distance of 50 centimeters. At a distance of 50 centimeters. At a distance of 50 centimeters. What is the linear charge density? What will be the linear charge density? What will be the linear charge density? Remember I told you guys that for a line of charge, the electric field due to the line of charge is electric field, and this is distance, this is arrow. So for an infinite line of charge or a line of charge or a charge wire, electric field is lambda over 2 pi epsilon naught r. I gave you this formula before. And I told you that this lambda is empty as 2 pi epsilon naught r times E. Now this one is called linear charge density. That's lambda we're looking at. We're told to look for the linear charge density, which has lambda. This lambda represents the linear charge density. So this is the same thing as 50 over 100. That is 0.5 meters. So this will give us 2 times pi, is 3.142 times epsilon is 8.85 times 10 to the power what? Minus 12 times our arrow is 0.5 times the field is what? 4 times 10 to the power what? 5. So we solve this very well. You are going to have 1.11 times 10 to the power minus 5 coulomb per meter. That will be the linear charge density. So let's look at one more question before we go. Let's look at one more question before we go. One more question before we go. Okay. Charges Q1 equal to 12, let's say plus 12 microcoulomb, and Q2 equal to minus 14 microcoulomb, and are enclosed inside a closed surface. Are enclosed inside the surface. Obtain the total flux leaving this surface. Obtain the total flux leaving this surface. Obtain the total flux leaving this surface. That is Q1 equal to this, Q2 is equal to this. Are enclosed inside a closed surface. Are enclosed inside a surface. Obtain the total flux leaving this surface. Very simple. Remember, total flux leaving the surface is equal to what? Total charge over what? Epsilon naught. So the total charge here now will be what? What will be the total charge? 12 micro. Okay, that's 12 plus what? Plus minus 14. That will give us minus 2 microcoulomb. We same thing as minus 2 times 10 to the power minus what? Minus 6 coulomb. So you don't remove the charge, solve with the sign. You don't remove the sign. So because we are electric field flux is a scalar quantity. So the flux now will be, equal to the net charge, which is minus 2 times 10 to the power what? Minus 6 over 8.85 times 10 to the power what? Minus 12. So this will give us minus 2.26 times 10 to the power 5 Newton meter square per coulomb. Newton meter square per coulomb. This will be the answer. So, what is it called? The flux leaving that surface, holding these charges. So please and 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 please help me to solve this question. Obtain the total number of field lines. Obtain the total number of field lines leaving a surface holding 1 coulomb of charge. Obtain the total number of field lines, that's electric field flux leaving a surface holding 1 coulomb of charge. Holding what? 1 coulomb of what? Of charge. Holding 1 coulomb of charge. Answer is going to be answer is going to be either 1 over 8.85 times 10 power minus 12, or 1.13 times 10 power 11 Newton meter square per coulomb. That will be the answer to that. So try and solve that and look at other questions regarding this topic online. See you guys in our next class. God bless you all.